All right, lecture 3, forces on planar surfaces. Okay, so our objective today is to apply the hydrostatic law to evaluate the magnitude and location of resultant hydrostatic forces on planes. And so for now, that's going to sound like a bunch of gibberish probably. And so let's remind ourselves real quick what the hydrostatic law is. And I'm going to kind of draw a picture and we'll kind of talk about what this means. So we want to remember that the hydrostatic law, as we, kind of at its most general, okay, is dp dz equals negative gamma. Okay, so this is it at its most general, and basically it says that as you move downward into a fluid, okay, that as you move downward in a fluid, the pressure increases. The change in pressure equals, well, generally it's, if gamma is constant, it's gamma times the change in z, okay, so, or negative, okay. So this is if gamma is constant, okay, and so that's what it says. So generally speaking, like if I were to draw a, a dam or something along those lines, and, that dam is holding back some water, right? So there's some water on the left and on the right it's just air. What we can imagine is everywhere in the air, okay, there's an atmospheric pressure, okay? So generally speaking, the atmospheric pressure, 101.325 kPa, okay, or if you want to use the English system, 14.7 psi. Okay, so what that means is that on the right-hand side of this dam, we just have the same atmospheric pressure just acting the whole way down. Okay, so we can see on the right-hand side we've got this pressure from the atmosphere, and it's pushing on the dam to the right, and it's at PATM. Okay, so now you might say to yourself, wait a second, you just said the hydrostatic law said that the pressure increases as we move, downwards. So in the fluid, so in this case, the fluid is the atmosphere, it's air. But remember, in problems with water, the gamma of air is so small compared to the gamma of water that basically the hydrostatic difference from the top of the dam to the bottom of the dam is so small compared to what's going to happen with the water that we don't worry about it. So there is a slope to this line that I just drew, like down here. The pressure is generally higher at the bottom of the dam. The atmospheric pressure is higher, but it's so the difference is so minimal that we don't even worry about it. Okay, so the atmosphere is pushing on this dam all along this right-hand side. Okay, and if I look at let's zoom in a little bit. If I look at the left-hand side, okay, we notice that we have over here, we also have atmospheric pressure on the part that's, at the surface, okay? So this is, so remember the atmospheric pressure is either 101.325 kPa, excuse me, that's a capital P. Oh, it looks like this, lowercase k, capital P. Or it's 14.7 psi absolute, so those are both absolute, okay? Or the last thing, and we'll talk about this in a second, or we can make this zero gauge, and we'll talk about this is obviously the preferred way to do it. And we'll talk about how it is that we make that work here. Because you're like, well, clearly, this force right here, all of this, clearly has an effect on this problem, right? So we'll talk about that in a second. Anyway, so at this point right here, okay, if we're going to follow the pressure moving downwards, okay, we remember this rule right here. dp dz equals negative gamma, okay? So as we move downward in the fluid, okay, if the gamma is constant, so we're going to assume this is one fluid, it has the same specific weight the whole way down, then what's going to happen is the pressure is going to increase linearly, okay, and the slope of this line is gamma, okay, and so it's going to increase as we move downwards through the fluid. Okay, if the fluid had different, if the density changed as we move downward through the fluid, it would slowly increase. The slope of that line would increase. All right, so now we've got, basically I'm kind of splitting this into two forces in some ways. So the force that we started with was this atmospheric force, which accounts for this first bit of it. But then the fact that we're in the water, okay, is basically increasing that by some amount. Okay, so I drew a little dotted line to kind of separate these two. Okay, so note that what we can do here, well, let's not worry about what we can do here, but the reason that we can use this zero gauge right here is that what I do is instead, if I'm working this problem, and I'll do this in red, so hopefully it'll be visible, But what I do is I note that the atmospheric pressure portion of this problem right here cancels out directly with this atmospheric pressure there. So I don't even need to think about it. Okay, if I'm looking for the net effect of the water on the dam, or I want to know the net force on this dam and how strong the dam has to be and what kind of forces it has to hold up and whatever, I can make note of the fact that all of this force over here cancels with this force over here. So instead of worrying about it, I'm just going to call this thing zero gauge. Okay, noting that this bit right here, okay, which is underwater, okay, I'm going to count as equal and opposite to that bit. So basically, when I redo this, I'm going to treat the atmospheric pressure as 0 right here, gauge, and then I'm going to ignore all the atmospheric pressure over here and the stuff on the left-hand side, and I'm just going to draw my line like this. Okay, so now I've ignored the hydrostatic effect, the atmospheric pressure on both sides of this thing. Okay, and that makes my life much easier. Okay, and so that's how we're going to evaluate this problem. Okay, so what we want to do in order to solve this, though, is we want this to look like a statics problem. Okay, so let's zoom out and I'll kind of describe that, and I'll redraw this, and I'll kind of describe what we want this to look like. All right, so here's the dam, and what I want to do is I don't want to consider all this nonsense that I put up here, on the upper drawing. So in the upper drawing, before I continue, this right here, this little drawing, this is called the pressure prism. Okay, so you may hear me mention the pressure prism again here and there. Okay, and it's a good idea to draw the pressure prism. It kind of gives you an idea. But the thing is, it's hard to work with a pressure prism, right? Because you can imagine that this pressure prism is, or could be represented by forces, right? In fact, it is a distributed force. It's just that, it has a low distribution here and a high, or lots of pressure at the bottom, no pressure at the top, okay? And so instead, what I want to do is I want to draw it as a single force, okay, which typically is called F sub P, force of pressure. At least that's what I call it. I actually don't know what your book calls it. Give me 1 second. Okay, it looks like your book uses F sub R for force of resultant. If you look in my old homework assignments, I'm always going to call it F sub P because I'm used to thinking of it as force of pressure. So either one of these is fine. But anyway, we want to replace all of this entire pressure prism with a single force. Okay, because once I can replace this with a single force, this becomes a statics problem, right? It's like fairly easy. Well, assuming we know statics. And so that's going to make our lives a lot easier. So we're going to replace all of this pressure prism with a single thing. And so to do that, we need to be able to, or in order to be able to use that, we need to do a few things. So first of all, for this FR, okay, we need 3 things. One of these is easy, and the other 2 are a little bit more difficult. But we need 3 things. We need the magnitude, okay, which is a little bit hard, the direction, which is the easy one, and the location, which is a little bit hard, okay? So as I move into this, okay, I want to mention a few things. First of all, this is the thing that most people have the most trouble with in this course. And so I'm really glad to do this one via video so that people can go back and watch it again. In the comments, I'm going to try to post videos to some other people solving these things. Because if you can't understand it when I do it, maybe you can understand it when they do it. But this is, for me, when I took this course, this part made sense to me. But then, when we got to momentum confused me. But for my students, most of them, this is the one that drives them the most crazy. So let's be intentional and let's be intelligent about this and let's focus because this is going to be one of the hardest things to do. All right, so the first thing is this, okay? F sub R, okay, the magnitude of this thing. Okay, so one of the easy ways to do this, okay, is if we remember that pressure, a pressure force is generally that pressure times the area. So if I look over here at this pressure prism as I've drawn it, okay, so that pressure prism over there on the left-hand side, Okay, if I knew the average pressure over the whole thing, okay, then what I could do is I could say, oh, well, if I take the average pressure, so I'm going to put a line over my pressure, I'm going to multiply it times the whole area. Okay, that would make sense, right? If I can find the average pressure as, as defined average over that area, then I can multiply by the whole area and I get it. Now the problem, of course, is how do I get this average pressure? Okay, and without going through a lot of proof of that, the way to do it is you take the pressure at the centroid. Okay, so the way you would get the pressure at the centroid is that is going to be gamma h bar. Okay, where h bar, okay, times the area. Okay, where h bar is the depth to the centroid. Okay, gamma is the specific weight of the fluid, and A is the area of the face. Okay, so what that means is the area in this case of, for example, this dam is if I were to look down here, it is this face, or at least a portion of it that's underwater, right? So let's be very clear about that. The portion that's underwater, there's no reason for it to be affected by the portion that's not underwater. Okay, times, whatever the width of this thing is. Okay, so if I were to kind of quickly sketch that in, okay, so I don't know, like that. Oh boy, I'm doing not a great job. Okay, so if this were my gate, then it would be, this face right here. Okay, let's see, it would be like this. Okay, as best I can draw it. Okay, so it would be whatever this depth is, okay, times whatever this width is. Okay, and that would be that area. Okay, so it's the area of the face that the water is pushing on. Okay, so if we take the average pressure and we multiply it by the area over which it's acting. Okay, so generally centroids, which I don't know how much you guys have worked on since statics, but generally any centroid, so the centroid of x, okay, is basically defined as 1 over the area times integral of x over dA. Okay, so this is generally how we find these. However, in fluid mechanics, what we do is we use a table. Okay, so let me find that table. So in your textbook, where you're going to find it is you're going to find it in figure 3.32. Okay, and so what it's going to do basically is it's going to tell you like, all right, so you're going to look at this, say this dam right here that I've drawn over here, or a different dam. So in this case, it's a rectangle, right? If you look at it, if you're like swimming, so I always like to draw the little eyeball, okay, and you look at it and you see a rectangle. Okay, then what you're going to do is you're going to go to this figure right here and you're going to look up a rectangle. And what the rectangle is going to tell you is like, oh, the centroid is halfway down this rectangle. Okay, you're like, okay, cool. So then I need to figure out where that is for my drawing. Okay, so like over here, I'd say, okay, well, it's halfway down. Okay, so I want to know this depth to that centroid, so I'm going to measure from there to the surface. Okay, and that's how you do it. Now, that seems fairly straightforward, but and it is with a rectangle that's going straight up and down, but sometimes these things are going to be like this. Okay, so if the rectangle is shaped like that, then you need to find the centroid here, and then you need to measure it this way, which means you're going to need to do some trig. Okay, and we'll do an example like that as well. Okay, now so this is how you get. So this is the magnitude. I should have labeled this. This is how you get the magnitude. Okay, and so ultimately, and I'm going to what do you call it? I'm going to summarize all of this before we move on. But what I want you to note here is that this is an equation that basically it's one equation. Here and here. And there's only 2 equations in this whole thing, and yet this still throws a lot of people off. And I'm going to kind of walk through how I solve these once we get there, but people get very confused and very turned around. So, focus and make sure that you can kind of understand what this is. All right, now if the surface of the liquid, of the fluid, is pressurized, okay? So if the surface is pressurized, then everything changes, right? Because if you look at my pressure prism over here, okay, all of a sudden everything, we don't start at 0. So we don't start at 0 right here as I've drawn it. So if this were pressurized, then what that's going to do is that's going to shift everything to the left. So by however much. So maybe it goes over to here. Okay, maybe it goes over here. Depends on how pressurized it is. Okay, so what it does is it adds a certain amount of pressure to it. So maybe this is, we'll call it P surf. Okay, the surface pressure is now no longer 0. It's some kind of value. So then what happens is, if we go over here, then the magnitude becomes FR equals P bar A equals, oh, come here. Oh, son of a, yeah, it's killing me. All right, equals gamma H bar plus the pressure at the surface, okay, times A. Okay, and the way that I mean, this is the same as before. It's just that, you know, before this was a 0, right? So this is kind of more general than this rule up here. But in this course, we're almost always going to use this one right here. So, all right. So let's put this in our like bag of tricks. Maybe I'm going to put a bag of tricks over here. Okay, we'll call it the bag o' tricks. Okay, and the first one is that FR equals P bar A equals gamma H bar A. Okay, so that's the first thing. And that's for the resultant force, so the magnitude. And I'm going to call that, and I'll explain for a second why, in a little bit, why I keep that one, okay? Because sometimes you don't have to go this far, and I'll show where in a second. Okay, so that's the first one, or the first thing that we need. Okay, the second thing that we need is the direction, okay? And the direction is the one that I say, anyway, is easy. Okay, and that's this. F sub P, or R, is always perpendicular to the face. Always. Okay, so you see I drew it up here. It's going straight into the face. Okay, so perpendicular. Okay, so that doesn't even go into our bag of tricks. Maybe I could say FR perpendicular to face. Okay, I don't even think we need that one. But I mean, you should just memorize that and learn that. Okay, pressure is always perpendicular to the thing that it's pushing on. That's just how it is. Pressure does not create shear forces. Okay, so we can't go there. Okay, now the last one is location, and the location really throws people off. Okay, so location. Okay, and I'm going to do a little drawing for this one, if it will let me scale around. All right, so the location of the force, okay, is at the center of pressure. Okay, and this is the point where I think things start to get confused. Okay, the center, because now we have two kind of like centers. We have a centroid, which is where the average pressure is, and then we have a center of pressure, which is where the pressure acts. Okay, and so what I've drawn here is, let's imagine that our problem had something to do with, I don't know, some sort of underwater gate, right? So we imagine, for whatever reason, maybe this is a dam, maybe it's a levee, and maybe every now and then they want to relieve pressure on the dam, so they open this gate up and they let the water flow through. Okay, but in the meantime, you know, the rest of the time, it needs to hold up to whatever the forces are on this thing. So they're like, okay, we need to make sure that it can hold. Okay, so I'm going to show you where things are, and I'm going to talk about things, and I want you to try to gain some intuition before we focus on what these things are. Okay, so the first thing is this, right? The pressure at the surface, I'll do this in green again, is 0, right? The pressure right here, okay, at the top of this thing is determined by how deep it is. Okay, it doesn't have to do with how far along it goes this way, because the horizontal has no effect. It only is affected by how deep it is. So the pressure right here equals gamma times whatever this depth is. I don't know what we'll call it. We'll call it H1. Okay, H1. Okay, the pressure right here, okay, is gamma times, I'll call it H2, right? So that's this depth right here. So the pressure anywhere on this gate can be found by just multiplying gamma times the depth, okay? Because I'm working in gauge, and I'm assuming the pressure at the surface is 0, okay, 0 gauge. Okay, if I wanted to, I could work in absolute and I could add, the absolute pressure. So I could add PATM here if I wanted to, but I'd prefer to just work in gauge and call that 0. Okay, so that's one thing. So then somewhere along here, there's a depth where there's a centroid here. Now, if this is a rectangle, it's going to be halfway down. Okay, and so if this is the centroid, then this is H bar, and the pressure here equals gamma times H bar, okay, just like any other location. Okay, so if I were to draw this pressure prism, okay, it's going to look like, let's see, it's going to look roughly more or less like this. Okay, with the pressure increasing as I move down this gate. Okay, so there's our pressure prism. All right, now, okay, so if I take this pressure, the pressure at the centroid, so this is the average pressure over the whole gate, and I multiply it by the area, okay, I'll get the total force, okay, the magnitude of the force. Now, that's cool. Okay, now then there's the next bit. Where does it act? Okay, and I want you to think about this like if I had, let's say I'm going to draw a little arrow and see if I can't move it around, right? And so let's suppose I took this little arrow, okay, and I were trying to come up with a space to put it such that if there were no forces in the universe other than this force, that is my little green arrow, and it's going to try to balance this pressure prism, right? Where do I put it so that the moments add up to 0? So like if I put it at the centroid, right, is that going to balance the moments? Okay. And hopefully you see that if I were to do that, that wouldn't work, right? Because if I put it right there, these forces on this side are smaller relative to the forces on this side, okay? And what's going to happen is it's going to want to spin. Okay, so ultimately the location that this thing is going to have to be is it's going to have to like go this way a little bit to account for the fact that there are larger forces on this side, well, on this side, if I could draw it over here, than there are over here. Okay, so the center of pressure, okay, is a little bit deeper than the centroid. Okay, and the way we define that mathematically is like this. Okay, let's see. The center of pressure is defined this way. YCP equals I bar, okay, over Y bar A plus Y bar. Okay, and sometimes you will see this written another way. Sometimes you'll see YCP minus Y bar equals I bar Y bar A. In fact, I don't know which way your book writes it, but either one of these is fine. Okay, wait. So your book writes it as YP minus YC equals IXX over YCA. Okay, where C means centroid and P means center of pressure. Okay, so if you look through my old notes and my old homeworks, I use this notation because that matches the old textbook. Okay. Anyway, so and you're kind of like, wait a second, Y's, but we've been working with X's. So what is all this business? Okay, so let's go down here and I'm going to draw the Y's. Okay, and this is where things get confusing for a lot of people. Okay, so here we go. So we're going to start at the surface here. So basically, H's, okay, measure downwards from the surface. Okay, those are depths. Okay, so H's are depths. Okay, Y's are kind of like distance from surface, but along the face. Okay, so if we start right here at this red dot, okay, and I move along this way, okay, then this right here is the YC or the Y bar, depending on which system you use. Yeah, so speaking of which, this is HC in your book. Okay, so yeah, so YC or Y bar, and so we follow it along here, okay, and that'll give us the Y centroid. And then to get to the YP, okay, we're going to go down a little bit further to wherever, oh, here's my green force right here, okay, so wherever that is. Okay, and that total distance from here to here, that's yp or ycp, depending on which book you use. Okay, so that's a little bit complicated, right? So there's like kind of a lot of stuff going on here. Okay, so let me go over here to my tools, and I'm going to kind of put this all in one spot. What color were we using over there? White. Okay. And what I'm going to do here is I'm going to erase these things. I'm going to put them all in the terminology of your book. Okay. And so we'll use y center of pressure minus y centroid equals ixx comma c over y. Sorry, it's hard for me to think in terms of this other notation, but you know, it's all the same. Okay, and now we'll do the same up here, and what I'll do is we'll make this HC. Come on, you can erase, you punk. You good for nothing, low down. Okay, so we'll call this HC. Okay, and this is the whole thing. Okay, this is the whole bag o' tricks. Okay, and now just to kind of give you an idea here, I'm going to draw, you know, just so that all of the bag of tricks can be together. Okay, so I've tried and failed kind of, but, you know, did the best I could to draw. Let's imagine like here's a levee or something. This is, let's say, a levee, and there's a triangular gate. Okay, triangular gate. Okay, and so I want to just define these terms so that we understand kind of what's going on here. Okay, so H sub C. Okay, so we're going to identify 2 points on here, one of which is the centroid. The centroid is going to have 2 points that we care about. Okay, one is going to go along the face to the surface. Okay, and that's going to be, so let's see if I can't label and give that a nice color. We'll call this, we'll put blue there, and I'll go this way, and I'll say that's the centroid. Okay. And it's got 2 values we care about. One that goes vertical to the surface, so maybe it goes up to like right about there. And the other one that goes along the face to the surface. And so the one that goes along the face to the surface, this is y sub c, y to the centroid. This one is h to the centroid. Okay. And then where the force acts is going to be at this red dot, a little bit deeper. It's always a little bit deeper. Well, it could be at the same spot, but and that only happens when the gate is like flat, so it's parallel to the water surface. And this right here is going to be measured this way. Okay, and that's y. Usually I call it YCP, but this book calls it YP. Okay. So those are the quantities that we're looking for. So this is our whole bag of tricks, if you will. All right, so that said, let's work a problem. And this is the whole thing. This is everything. Okay, so if you are stuck and you're doing homework or something, like, you know, write all this out. There's nothing else you have to think about. Okay, now I'm not saying that this is nothing, okay, and I'm not saying it isn't confusing, because dealing with all these different distances, but there's only 3 of them. The depth to the centroid, the I guess along face distance to the centroid, and the along face distance to the center of pressure. Okay, I will note also that this distance right here is right between, this is how far it is between YP and YC. So that's this distance right here. Okay, so it can be a very small number. Sometimes it's 0, but it's only 0 if the gate is completely flat. All right, so I'm going to go and I'm going to do an example, and I'll probably grab this bag of tricks and bring it down and show you how we use it. So bear with me while, well, you're not going to have to watch me draw, because that would be annoying, and you have things to do. And we're 30 minutes in, and I've got a couple of problems that I want to work, so let's do this. All right, so we've got some system here. We'll draw the water a little bit longer than that. We've got some system here where there's a gate, okay, and there's a hinge on this gate. So here's the hinge in yellow. Okay, so there's a hinge. And you can imagine this gate, which is this double line thing that I've drawn. And for whatever reason, it's at the bottom of this wall. I don't know who makes these problems. Anyway, this is a very, very, very typical problem. What they want to know is they want to know what is the force at the end of this gate. Okay, so what that means is, in this case, I'm going to make this up. I'm going to assume that we're talking about a horizontal force. So basically, if we look at this spot right here, right, that's the only support on this gate. Okay, that's the only place where this gate is being supported. So what we want to know is, like, how much force does this wall have to support at the end of that gate? Okay, and you can imagine we're under 15 feet of water. In fact, I didn't quite tell you, but this is salt water. Okay, salt water, which is a little bit annoying. Okay, and so in this case, gamma is 64 psf, so it's a little bit more dense than freshwater. Freshwater is 62.4. Freshwater is 62.4. Saltwater is 64 psf. Anyway, so we need to figure this sucker out. Okay, so what we're going to do here, and this is really important. This is a very common thing. So we want to know what's the force of the hinge and what's the force that has to support this thing. Now, anytime in my class where you're going to do, not necessarily on a test, but if I ask you to turn in one of these problems, and I will, you have to draw a free body diagram because we're going to be summing forces to solve this. So anytime in this class where you sum forces, you have to draw a free body diagram. I'm sorry, there's just no way around it. A lot of my students like to avoid it. It doesn't have to be a beautiful free body diagram, but that's how we solve problems. So let's go right here, and I'm going to write solution like this, just an S and a dot, solution. And the first step to that solution is a free body diagram, okay? And it's not going to be a complicated free body diagram. I don't want you spending all day doing this, but you do need to make sure that you have all the forces included. All right, so what are the forces on this sucker? Okay, and well, we've got a hinge, so typically I like to make those forces like this. I like to make them both in the positive direction because that just makes my life easier. And I'm going to call this hinge in the Z direction, and I'm going to call this hinge in the X direction. Okay, you could call them whatever you want to call them, right? The next thing I want to do is this force right here. I want to make sure that we include that, so it's going in this direction. And that's going to be F, I'll just call it F. Okay, that's the one I'm solving for. Force at the end of the gate. I could call it F, E, G, F end of gate. It doesn't matter, again. And then the last one is, okay, I note that there's a pressure prism on this thing. Okay, so the pressure here, remember, is going to be P equals gamma times whatever the depth is right there. Okay, so I don't know what we call that. I think in my drawing earlier I called it H1, but we're not solving for that value, right? But there's a pressure prism here, okay, and it's getting deeper. The pressure is increasing as you move downwards. But I don't want to think about that pressure prism because I can't solve that, right? I want to go and I want to replace that with a force, which is going to be more than halfway down this sucker. And I'm going to put it just like right here. Right now I don't know where it is, okay? But I'm just going to kind of draw it here. So this is F sub R, okay? So I'm replacing all of this with a single arrow, okay? So that's kind of the nature of this beast. So what I want to do now is I want to take my bag of tricks from up here. Can I get just the bag of tricks, you punk? I cannot get just the bag of tricks. Okay, so let's just put that there. And that'll remind me kind of what it is we're working on here. Okay, so I've now screwed up the whole thing here. So what we need to do, and I'm going to do it the same way every time because I find that this is the easiest way for my students, is we want to think about, all right, the way I do this is I write down the word shape, okay? And in this case, so the first thing I want to do is I want to think about what kind of shape am I looking at here? Okay, so if I'm swimming in this water, so if I zoom in on this picture, and I'm swimming in this water, so, and I have an eyeball right here, okay, and I look at this gate, what do I see? Well, it's 5 feet wide, and it's got some distance from here to here. Okay, it's a rectangle. Okay, so I'm going to say, oh, well, it's a rectangle. Okay, that's one thing to write down. Okay, so it's a rectangle. Now, what does that rectangle look like? Okay, well, it's 5 feet wide on the bottom, 5 feet wide on the bottom, and then it's whatever this distance is tall. Okay. Okay, so, well, how tall is that? Well, this is a 6 by an 8 foot triangle. So we need to use Pythagorean Theorem. And this ultimately is a 3, 4, 5. So I'm not going to do the Pythagorean Theorem for you, but or you can just recognize it's a 3, 4, 5 triangle, and so that's 10 feet. Okay, so this rectangle is 5 feet by 10 feet, and it's submerged on an angle. Okay, so that helps us with a few things. So I'm going to pull up your book, and it notes that if you look in your book that the centroid of a rectangle is right in the middle. So it's going to be 5 feet from either side in this plane, in the slanted plane, in this plane right here. Okay. And then, let's see, so that's the centroid. So the centroid is 5 feet from either thing. So this is the centroid. Centroid. Okay. And then, yeah, so now we need to start getting quantities. So if I look at my bag of tricks, okay, we are going to need a few things that are going to come from this shape. I need to know HC. I need to know the area. I need to know the YC. And I need to know the YP. Okay, so that's just looking at these equations and figuring out what things I need. It's always the same things. So the easiest thing here is the area of this face. Okay, and that's, if you look on your chart. So again, this is all coming from figure 3.332 out of your book. Let me make sure I got that right when I said earlier. Yeah, 332 right here. Okay, so this is all coming off of that. So, if I gave you an unusual shape. So they're not all going to be rectangles, although rectangles are pretty common. If it will let me zoom back in over here. Okay, so the area of a rectangle is base times height. So in this case, it's 5. So it's going to be BH, base times height. So that's going to be 5 feet by 10 feet equals 50 feet squared. Okay, now, all these others are a little bit harder than that. The centroid is 5 feet down this face. I want to go look at my original picture. So it's 5 feet down this face here, okay, to here. So you're like, all right, well, the HC is going from this point to the surface, okay? So if we zoom in here, this gets a little bit complicated, but only a little bit complicated. Okay, so you're going to have to be able to do some geometry here. So I'm going to do it in yellow because it's going to match my earlier stuff. So this is 6 feet, remember? Okay, this guy right here, by similar triangles, okay, because it's halfway down, this is 3 feet right here, 3 feet, and it would be another 3 feet to the bottom. Okay, and then if we note that the whole thing is 15 feet from over here, okay, then this right here is 15 minus 6 is 9 feet. Okay, so then this distance from here, so H sub C is the depth of the centroid. So it's going all the way like this. Okay, so that's going to be 12 feet. Okay, because it's 9 plus 3. Okay, so we can go over here and we can say HC is 12 feet. Okay? Now, to get the YC, okay, it's the same point. It's the same point, but now we have to measure along the face until we hit the surface. So it could be like this, all the way up to here. Okay? So I want to note that there's a few ways to get this. Okay, one is kind of like what I just did, and it's using a bunch of similar triangles. So I can note that, let's see, what color is going to show up right now? Red. So I can note that I can go from here to here is 5 feet, because I found that from over where I did the shape. So that's this 5 feet right here. Okay, and then I just need to figure out the rest of this thing. Okay, and I can note that this triangle is a 3, 4, 5. Right, noticing that the, so this is a 3, 4, 5 also. Okay, noting that the vertical side is the 3, so this is the 3. This side is the 4, and this side is the 5. Okay, so if this is the 3, so we take 9 to, so this is basically 3 times 3 gives us 9. So this is going to be 5 times 3, so this is going to be 15 feet. Okay, so if this is 15 feet, then I can add 5 feet here, and I'll get 20 feet. Okay, so that's one way to do this. Okay, Now, some of you are not going to be comfortable with that, okay? Some of you, are just like, you know what, just give it to me in sines and cosines and do the rest of it. So what you could do that in that case is, if you prefer that, you could say, you know what, what's this angle right here? And well, let's see. So this angle, we know 6 feet here, we know 8 feet here. So that's going to be a tangent. So I can say inverse tangent of, let's see, the opposite over the adjacent, 6 feet over 8 feet. So you can get that angle. So that's theta. And once you have theta, you could do theta as right here as well. Okay, and then you can say, okay, well, I want the hypotenuse right here. Okay, and I know, and I know this because I just solved for this earlier, right? This was 12 feet, I believe, right? So if you take this, the opposite, and this theta, okay, I can say, well, okay, I know, because you know theta, and you can say, okay, well then I need the hypotenuse. This is the opposite, so ka toa, so that's sine. So sine of theta equals the opposite, 12 feet, over the hypotenuse, which is what you're looking for. And if you solve that, h will be 20 feet, okay? So that'll also work out. So that's another way you can do it, okay? There's lots of ways. It's geometry, right? It's annoying, but it's a part of this class. All right, so then the last thing we need from this shape is actually, and I've screwed this up, is not yp. It is ixx, okay? And we get that from the table or figure 332. So I want this to be in white, I, x, comma, c, okay? And so what we want to do is, so if you look in the chart, the way this book has it, well, the way I like to draw it is 1/12. They call it AB cubed. I say BH cubed. It's the same either way. And so we'll do is 1/12, the base, which in this case is 5 feet, times h, which in this case is 10 feet cubed. Okay, and if we plug all that in, we're going to get, well, I never wrote it down. Hold on. Okay, 416.67 feet to the fourth. All right, now you're like, well, that was annoying. Like, this is a lot of bookkeeping. It's a lot of bookkeeping. Okay, but, and some of these quantities are harder than others, and there's a lot of geometry involved. But once you get here, things are going to start to make some sense. Okay, so again, let's grab our bag of tricks and let's bring them down. Okay, and let's put them next to our shape. Okay, because once you have this, okay, I think we should be pretty good to go. Okay, so if I want f sub r, okay, so here we go. Okay, now I'm basically going to do some plug and chug. Okay, f sub r equals gamma 60. Well, let me write out the equation before I go there. Okay, because it helps me. Okay, gamma HCA. Okay, well, gamma from the problem is 64 PCF, salt water. Okay, HC from right here is 12 feet. A from right here is 50 square feet. Okay, so the FR equals 38,400 pounds. Okay, I'm keeping 5 significant digits, so I guess I could put a dot right there. Okay, so then that's FR. Okay, the next thing we need, so we got this one taken care of. Okay, I'm going to undo that actually, just because I don't want it to, travel around with our bag of tricks. Okay, we know it's acting perpendicular to the face, and so the next thing we need to know is, where does it act? Okay, and so I'm going to say, well, YP, we'll do YP minus YC. I'll just follow the tricks of the trade here. Equals I XX comma C over YCA. Okay, so YP minus YC in this case is 20 feet equals IXXC equals 416.67 feet to the fourth divided by YC, which is 20 feet, divided by the area, which is 50 feet squared. Okay, check our units. We notice feet to the fourth is divided by feet cubed is going to give us feet. Okay, so we're going to end up with YC minus 20 feet equals equals 0.41667 feet. Okay, so what that means here, and I've kind of left it drawn in this kind of awkward thing. So basically we're looking for two numbers. Okay, but what this tells us is that it's acting 0.41667 feet further along the face than the centroid. Okay, so it's a little bit deeper. It's acting at 20.41667 feet from the surface if we travel along the face. Okay, so, and it has a force of 38,400 pounds. Okay, so I'm going to go up to my, to this thing right here, to my free body diagram, and if I'm really careful with my erasing, I can, get rid of some things that are annoying me. But, yeah, I'm not going to be able to not get that. Okay, that's okay. All right, so now this is a statics problem, okay, which is nice. We like statics problems, okay? Statics problems should be our bread and butter at this point, okay? So what I'm going to do, I'm going to go over here, and we're just going to start. So, at this point of your engineering career, you should know that if we're dealing with a statics problem, we have three equations, right? We have sum of forces three equations if we're in 2D, which we are. Okay, so I'm going to start by saying, let's see, what do we want to do first? Oh, well, first let's figure out where this force resultant is acting. So what I'm going to do in this case is I'm probably going to sum moments around this hinge, because that's the only way to solve this problem, right? Because I don't know hx and I don't know hz, so I can't sum the moments around there and expect anything to work. So I need this distance right here to solve this problem, okay? Now what I know is that my, to the depth to the centroid from here, not depth, but my along face distance all the way down here, okay, is 20 point whatever it is, okay? So 20.41, so that distance is 20.41667 feet, okay? I need to know this distance here. Okay, so in order to do that, I need the total distance, and then I need to subtract out that. Okay, so the total distance, again, you could do that with theta if you prefer the trig way. I prefer to note that this is the 3 side of a 3, 4, 5 triangle. So if this is the 3 side, and this is the 5 side of the 3, 4, 5 triangle. Okay, then it's just a ratio, so it's like 3 is to 5 as 15 is to what, right? So it's going to be 25, okay? So the whole thing, this whole side is 25 feet. So if I do 25 minus that number, I'm going to get, 4.5833 feet, okay? Again, keeping 5 significant digits. So this distance right here is 4.5833 feet, okay? So now, what we want to do is, the first question was, what are our questions here? Oh, force on the end of the gate. So we want F. Okay, so now we're going to do so how do we get F looking at this free body diagram, which I really should have put somewhere where there's a little bit more, space, but I didn't. Or really, I drew up all on it. But so we're going to sum the moments. So I'm going to do sum of the moments I'm going to go around the hinge, equals 0. Okay, and I'm doing that because that gets rid of these hinge forces, which I don't want to deal with, and it allows me to solve this problem. Okay, so I've got this FR, and it's going to be multiplied by its moment arm, which in this case is 4.5833 feet. Okay, and that's causing a force to go in this direction, so that's clockwise, so that'll be negative. And then we're going to add F, which of course is causing things to go counterclockwise, so that's positive, and its moment arm. Now, there's two ways to deal with that moment arm. The way that I recommend is doing this kind of a projection of that force this way. Okay, so that F is now in a right angle to our fulcrum. Okay, and so we need to know the vertical distance to where F is. So if we go over here, that vertical distance is 15 feet. Okay, so we're going to go F times 15 feet equals 0. Okay, noting that this one is positive because it's going in that direction. Okay, so if I plug in numbers, we can solve this. Okay, and well, the solution ends up being 29.3 kips, but I made an error right here. That should have been 6 feet. Okay, so if we go back to our free body diagram, we note that it was actually kind of given in the problem that it was 6 feet to the top of this gate. So that was the vertical distance. Okay, so that's how you solve it. Now, at this point, I imagine some of you going like, wow, that was a lot. Okay, and it is. It's a lot. Okay, these require practice. Okay, and the hardest thing here for a lot of people is, just the geometry. Like, it's not something that, this is some very intense geometry. Like probably more intense than we've had to deal with in a long time. So, all right, so I'm going to do another example. This one will not be a rectangle. Okay, this is, pretty hard. Okay, let's see if we can drag our bag of tricks around. We can drag our bag of tricks around. So let's drag them kind of over here. Well, we'll drag them wherever we need them. But I'm going to draw another problem. And yes, you're going to need some examples on these. And I mean, they're not easy. So let's do it. All right. So we've got, to the best of my ability to draw, a horse trough. Okay. So you can imagine this is is it a semicircle? A half a circle? A hemicircle? Semicircle? Whatever. It's a half of a circle on the front and the back of this thing, and it's full of water. Okay, it's full all the way to the brim. Okay, and we want to know, what is the force? What is the pressure on these ends? Okay, and where does it act? Okay, so we want the total force of pressure, F sub r, or I think they're thinking of that as a resultant force, and then where does it act? Okay, and so I like this one because, well, it's got some nice things about it. First of all, whenever the face itself is vertical, it's straight up and down, it's going to make your life a lot easier, just because the geometry is easier, there's less trig, et cetera, et cetera. But also there is, well, it's just going to make your life easier. But another thing that I like about this one is it's not a rectangular face. So whenever you have a non-rectangular face, these are typically a little bit harder than the other ones, okay? So I'm going to do this the way that I always do this. It looks like we don't need to do any statics on this one, so we won't need a free body diagram. So again, anytime you have to sum forces, even if you're just doing it mentally in your head, I'm going to want to see a free body diagram. In this case, there is no such thing because we don't need it, okay? Because we're not asked for any other forces. So so here's the solution, and I'm going to do it just like I did the last time. Okay. I'm gonna start by doing the shape, okay? So if I'm swimming in the water and I look at the face that we're thinking about, so in this case that's this face right here, okay? So what is that? Well, that's a semicircle, some kind of circle that's a half of one. And so what I can do for that is, well, let's see, so let's just draw it. Here it is, okay? And I know that it's 5 meters on a side. Okay, or 5 meter radius. Okay, so what I can do is I can go into, I can go to your figure 3-3032, and I can note, oh, they have a semicircle. It's not a hemicircle, it's a semicircle. Okay, so that's pretty cool. So the nice thing about finding that thing is it's going to tell me a lot of things that, I need to find. So there's 4 things I need to find, okay, always. Okay, and I'm going to put them in a different order because I think the area is the easiest one. Followed by probably IXXC, okay, followed by Y, I would like to call it Y bar, but Y the centroid, and H the centroid, okay. Well, those probably should go in the other order, but for this problem it won't make a difference. Okay, so the area of a semicircle is pi r squared over 2, okay, and that makes sense because it's a circle divided by 2. So that's pi times 5 meters squared over 2. Okay, so that's, we can punch that sucker into a calculator if you were into that sort of business. And we are all into that business because we are engineers. So, all right, so we get a number that is, whatever, fine, okay. And now we're going to do the IXXC. So if we look at the equation in the book, I really don't like their version of this equation because it's decimal, but whatever. I don't really have a lot of choice in the matter. Now, do I? We'll just use what they've got. That's ugly. Okay, r to the fourth. Okay, so I'll plug that in, 0.109757. Okay, times 5 meters to the fourth. 5 meters to the fourth equals 68.598 meters to the fourth. It's kind of a meaningless number, so definitely with this, like at least it's meaningless to me. I can't picture what a good value should be. So if I were you, I would punch that one into the calculator several times. Luckily in this case, I punched it in and it matched my old key, which means I probably did it right. So, you know, I'm kind of cheating in this regard. But normally I would punch this number in the calculator several times because it's kind of hard for you to picture, you know, what this could be. I can at least picture what this might be, okay, or what it should be, or something along those lines. So at least I can get in the right order of magnitude. This one, not so much. All right, so next we need y sub c. So y sub c and h sub c, I want to note that, so if my centroid is somewhere on this shape, let's suppose it's like right here, okay, the depth of that centroid is to go from there straight up to the surface, as always. And the yc is to go from that point along the surface until it hits the water surface. Okay, so note that in this case, when the face is vertical, these are the same. So I'll you know, same if face is vertical. Okay, so that's really important. Okay, so which means that all I got to do is go and look at the diagram in your book. Now I want to note that the diagram in your book doesn't it defines the centroid from here to here, which is actually really nice. Okay, if this semicircle had been shaped, if it had been upside down, okay, like this, we would have to get this distance, which would be the radius minus whatever that distance is. Okay, this would have to go right there. Okay, you know, x, whatever we want to call that. Okay, in this problem, this is HC or YC. Okay, but if the shape were upside down, you have to figure out, you know, which side it's on. Okay, so anyway, so in this case, we can solve that by, I'm just going to do these both at the same time because they have the same value, 4r over 3 pi. I also don't like the fact that they use capital R's, but whatever. Okay, so this equals 4 times 5 meters divided by 3 pi. Okay, 2.1221 meters, okay? And this one, at least, we can get an idea just kind of looking at it, whether or not that's reasonable. And it makes a lot of sense because this is 5 meters, right? And the centroid in this case, if we think about a semicircle, okay? So if it were a rectangle, right, it would be halfway down, so it would be like here, right? So if this were a 5 meter deep by 10 meter rectangle, then it would be right here, right? Now in this case, however, it's not a rectangle, right? And you can see that, like, where is the average depth? Well, the average depth, we've got more of these low-level values of depth than we do of these high-value depths, right? So the centroid is not going to be at 2.5. It's going to be up this way a little bit. Okay, and we found it to be 2.2 or 2.1221. Okay, so that makes sense. It should shift towards where the greatest area is. Okay, so note, like, yeah. So that's just the way it's got to be. Okay, so now that we've got these, in this case, 3 or 4 quantities, we can solve this. Okay, and this is kind of nice. Okay, so we go over here, and what are we looking for is FR on the end, so the resultant on the end, and where does it act? Okay, so that is. We have equations for that. Okay, so FR equals gamma HCA. Notice this is a plug and chug now. Once I have done this shape stuff, okay, this is plug and chug. Well, I just drew a line through one of my numbers. Okay, so I could pause it and just do the plug and chug. I won't do that. I will just go ahead and do these things for you, okay? In this case, I'm going to solve, because what it's asking for, well, let's just do FR, okay? So gamma, in this case, it's fresh water. So the density of fresh water, by the way, we should note here this, if ever you forget what this is rho times G, Okay, so the density of fresh water in the metric system is 1,000, and G is 9.81, so you just multiply those. It's as if you forget, and you get 998.10 newtons per meter cubed. Okay, HC, what we solved for that is 2.1221, 2.1221. Remember, always keeping 5 until we have to report it. Okay, and then area, which we discovered to be, again, 5 significant digits, 39.270 square meters. Okay, so the FR equals, okay, 817,520 newtons. And because I only want to keep 3 significant digits, we're going to make that 818 kilonewtons. Okay, boom. Right, so here's where we report. So where we report, we square it off. Okay, I always like to draw out all 5 significant digits one step earlier because just in case I need that number for a future calculation. But this is the one that would go in my answer. Okay, that's the one, if I was grading, that's the one I'm going to look for. Okay, so, and then what I want to know is YP minus, well, we're going to do YC plus IXXC over YCA. Okay, now in this case, I moved the YC to the right-hand side because the YP in this case is the depth from here all the way down to where it acts, which is exactly what I'm looking for. Okay, so if I'm looking for the location, it's got to be relative to something. So in this case, it's going to be relative to the surface. You know, if I told you it was like, oh, it's like 20 centimeters deeper than the centroid, well, that's not really very helpful. So we want it to something that's easy to visualize. Okay, so YP, I'm just going to start plugging in numbers from our shape thing over here. So let's see, YC is 2.1221 meters plus 68.598 meters to the fourth over YC, which is 2.1221 meters, okay, times the area, which is 39.270 meters squared. Okay, noting that the meters cubed on the bottom are going to cancel with 3 of the meters on the top. There's going to be 1 meter on the top, so I'm going to have meters for my YP. So keeping 5 significant digits, 2.9453. So if we were working with it, we would use this number. But if we're just reporting it, I would say YP equals 2.95 meters from the surface. Okay? So basically, you know, your answer would be FR equals 818 kilonewtons perpendicular to wall at 2.95 meters below the surface. Okay? And of course, if you needed to do any statics on this, like if you were like, you know, if the problem were like, well, this is a hinge or something, and you know you had to do statics, then you would use these versions so that you would have a little bit more, you know, guarantee that you weren't going to have any rounding errors. Okay, that's why I say to use 5. I mean, really 4 would be enough, and nobody you report to ever is going to. I can't imagine going to want more than 3 significant digits. So you know, usually I'll grade to 2, but my expectation is that you should get it right to 3. If you're keeping 5 all the way through the problem, you should be fine. Okay, so that's an hour 3. This is really intense stuff. I highly recommend that you read the book on this and look through their examples. There really isn't enough time for me to work another one. I might, because I know that this is a problematic for students, I might create like a supplementary lecture for anybody who wants to watch me just, you know, plow through these. Like if I just did like 4 or 5 of these in a row, maybe that would help you guys. So anyway, so that's all I got for this. Take care of yourselves, take care of each other. Please come to office hours. Nobody's showing up to office hours. You guys are texting me and emailing me homework questions. Just come to office hours, guys. I stare at a screen for 8 hours a week and nobody comes in. All right. Anyway, talk to you later. Have a good one. Bye.